All right, so over the weekend, you had a pretty short one problem. It was one function quiz, and you had to answer, I think it had M parts, however many, okay, Sky can't hear us. So however many parts A through M is, you had to answer all the parts about, here we go, page 13. What's the source on that one? In the input, come here, TV. It is this one that says source. It needs to go to HDMI2. TV, nap time. Anyway, the biggest thing was you had to get the question from the document I posted, and then at the same time upload it as a PDF. And I tried my hardest to express that in conversation before the weekend, but pre-calculus had a full-blown test over the weekend. So I'm talking like 2 chapters worth of a test due. So, but it was the same thing. They had directions, they had to download it. The directions were I thought pretty straightforward. That says you're going to submit a PDF file. You really should have only needed to do 1 file, even if you had 3 pages of work. There are ways that you can very easily convert 3 or however many pages of work to a PDF. And I tried to say, don't try it for the first time at 11 o'clock Sunday night. And if I didn't get like 20 emails from like 9 to 11:30 p.m. last night about this. But there's 100 of you trying to upload stuff, and everybody's learning, and I'm going to work with you the best that I can and taking things, but I'm not going to take 100 emails of, oh, my thing didn't upload, here's my email. I can't do that. I won't do that. So there's a place for you to submit stuff. If you have issues, there are apps that are free that help you take pictures, whether you have a smartphone or a mobile device, or I don't know, whatever else you would want to use. You can also, I don't think I can share this. Where did it go? Word. You all should have Microsoft Word, or even if you have Google, whatever the Google version of that is. You know, if you come and you insert any kind of picture, I mean, if you take the biggest thing is you have to take pictures of your work and send them to yourself somehow, and you have to download them. So I took pictures of my kids' work over the weekend, and I saved them to my computer, and I'm inserting the photo into, Mary, I'm gonna wait, Mary Gray. Okay, if you wanna stay after, we can, I don't care. But anyway, like my 3rd grader is doing addition with large numbers, but there's a picture of his work in his beautiful 3rd grade 8-year-old handwriting. But you can do that for every single page of your work, and then you can save it as a PDF. Like, you have that capability. It will save as a PDF. So even if you don't have an app, I know you all have Word, and again, whatever the Google, I don't know, Google Docs, even the Google Docs will allow you to export it and save it as a PDF. So point is, you really should have known how to do it. And a lot of people had trouble. Thank you for those that did upload it correctly. I don't want to lose sight of the fact that the majority of you didn't have any trouble with it, but I had enough have trouble with it that I thought it was worth mentioning, because, I mean, it only took PDFs. It didn't take JPEGs. It didn't take other image files. So I don't know what to tell you. But you show me your work, I'll grade them, and it moves. Yes?
Is it okay if we uploaded it as 2 separate PDFs?
So if it let you, you're lucky, because I thought it only took 1. But if it let you do 2, then that's fine. But moving forward, the goal is going to be 1.
Okay.
Because, like, to grade these efficiently, I have to download them, save them, grade them, upload them, attach them, and there's 100. I have 100 students that I do this with. So the most efficient way will be one PDF with your name somewhere in it. Because if everybody sends me Math Quiz 6, I'm like, oh, and you don't put your name on your paper because you're not really turning it in. So I'll try to make that a little more prevalent, clear,
Okay.
moving forward, with maybe a little more explicit directions for those who don't pay attention to things that we talk about in class or watch lectures. I still have people that aren't watching lectures and they're not coming to class, so I guess they're just teaching it to themselves. But yeah, we'll have, I think, other than maybe some practice problems that we may do a practice upload to see if you can follow the directions, just on like a practice take home. We'll see what I do. There's some problems that are coming up that are pretty lengthy. We'll do this section that we'll start today. We'll probably spend some more time on it tomorrow. And then we only have one more section that's not really, it kind of goes back to infinite limits that we did in chapter 1. We'll do it at the end. It's like the easiest thing you'll have. And then this coming weekend is Easter. So I know that most of you won't be able to celebrate it with large groups of family that maybe you would have before, or go to church, or whatever it is that you do for that. So there won't be anything due Friday, Saturday, or Sunday. But there is potential for there to be a test early next week, like test due by Monday, test due by Tuesday, and it'll be all of this chapter 4 stuff that we've done. Okay, but we got to get through this section today, tomorrow, and it'll be a lot like that quiz. It'll be a question where you agree to the academic integrity policy, and then it'll be a file where you open it. You will have maybe like 2 or 3 hours to do it. And then the expectation is that you take pictures of your work and send them within that same time frame. So we can practice it. We can practice it with some homework questions. I did already put up the guided learning in Sapling for 4.7 and the homework assignment for 4.7. I think there's only 10 questions, but it's a lot of work, and we're going to look at those today. So other than that, do you have questions on anything? The homework, I don't remember what I picked because I'm trying not to do, let's see, currently the 8th is Wednesday for the guided learning. It's really short. And then is that Saturday? I might change that to be due like Thursday or Monday. But it's only 10 questions, so you should be able to, I would start on it for sure. The guided learning, though, you should be able to do that by Wednesday. It's not really long at all. It's very easy, actually. It's like, what is the perimeter of this rectangle? And what is the area of this rectangle? It's pretty simple. Yeah, every day, work on your math every day. I don't know. I can only say it so many times. It's like I can talk about uploading and directions, and it's like I told my pre-calc students earlier, it's like I tell my kids, don't do that or you'll get hurt, don't do that or you'll get hurt, and they do it and they get hurt, and they're like, oh, you were right. You should probably not do that. So you should probably do your homework. Just a recommendation. Because the reality is, I don't know what the university is doing with respect to this whole pass-fail option for grading. We are not a fan from the math department because you need certain grades to move forward in math, and just to say, oh, you passed calculus, it's not really helpful. Plus, those of you that are looking to go into master's or PhD programs, or maybe, I don't have to go back and look at some of your majors. Some of those are really GPA specific, and giving you a pass that doesn't help your GPA is not helpful. So I don't know that a decision has been made, and when a decision gets forced regarding your grade, whether you opt in or opt out or letter grade or pass fail or whatever they decide to do, I will let you know, because I guess an email got sent about the options being discussed. So I'll let you know when I know, but I don't know anything about the grading for the university right now. All I know is we have a little less than a month left of class. We have more calculus to learn and talk about, and we're just going to keep moving forward like it's normal as normal can be right now. Okay. But I'm happy to help you all with this homework that was stressful and awful, but you have to start it before the day it's due. Because if you don't start it until then, I can't help you. And Math Lab can't help you, and tutors can't help you. And then you get frustrated and you lose interest and you're like, screw this, I'll just take the whatever. It's not healthy. So I'm happy to help you. And you have classmates, and I learned that you have Zoom and you guys can Zoom together. You don't even have to be with me. You can Zoom on your own if you wanted to video chat or Facebook, whatever, or whatever else it is that you guys use. But anyway, you have options if you would use them, and that's totally left up to you. I'll help you all I can from my end. I did video with a few I have over Saturday, Sunday, Friday, Saturday, Sunday. So you have to let me know. And I know it's Easter weekend and you can work all the weekend that you like. Paige says a few of them group FaceTime on the homework if anyone wants in. Add it. They can, I think you guys have access to each other through As You Learn. And that's fine. And if you were on there and you decided that you needed help, you'd be like, hey, Miss Puckett, there's a few of us doing this and we can do a Zoom pop-up. So you just let me know. I'll be happy to help you all that I can. I'm glad that this is sort of keeping you sane, Erin. It's I know it's not ideal, but we're trying to do the best that we can. And my kids hate it because they have to do work at home and it's terrible. And I'm sure you don't like it either. So, all right. So Paige has put her email in the group chat. If anybody wants to email her your phone number, and you guys can set up a FaceTime if you want, which I guess is an Apple thing, right? For iPhones. If you don't have an iPhone, you wouldn't be able to do that. So, but anyway, I welcome anything that you guys can do with each other that would help. Would be good. Or MacBook. Gotcha. Okay, so unless you have questions about the first 4.2 to 4. Whatever we've done so far, the increase, the decrease, the first derivative, the second derivative. I honestly think a lot of people's issue are the derivatives themselves and finding where they equal zero. This section is going to present more of that, but these are probably 95% word problems where you are doing what is called optimizing functions, optimizing scenarios. So this is going to be more like, I have so much fence that I want to build a rectangular area, and what are the dimensions to maximize area? Or I want to make this can and I want to minimize the cost of the materials to make it. Or what are some other ones? Minimizing distance, maximizing, we don't do a lot of cost. Sometimes we'll do cost functions. A lot of it is geometry, like volume, surface area, area, perimeter, and you will have those. You don't have to memorize them because I think most of your life they've been shoved at you on a formula sheet. But a lot of it has to deal with setting up, like you have to set up the problem. So a lot of people have trouble in this section. This is 4.7. We will come back and cover 4.5 towards the end of the week, but this is going along with minimizing and maximizing. So this is some steps that your book presents. And then I have this multiple page of examples, and we'll get through whatever we can get through in the next, what is that, 30 minutes? See what kind of questions you have. You can start your homework. But the steps, as bland as they may look, it has you read the problem until you understand it. But really the biggest thing here is your ability to that's a weird color. Let's do maybe yellow. Is to be able to identify the quantity that you're trying to optimize. So by optimizing it, you're going to either minimize something or you're going to maximize something. And you don't really have to like test stuff, because usually you only get one working number that is even helpful. And that's usually the answer. So there's not as much guesswork. But you're going to try to figure out, Are you maximizing area? Are you minimizing cost? Are you, those are the big ones, minimizing distance? So you're either going to maximize or minimize something. And if you remember from the last few sections, maximums and minimums come from critical values of the first derivative. So we're going to have a function, we're going to take its derivative, you're going to find the critical number, and that is going to be the value that minimizes or maximizes it. So step one is probably the hardest step, because you have to actually, or maybe step 1 and 2 combined. A lot of pictures get drawn, but you have to understand the equations that you're working with and what it is that you're trying to solve for. So, and then in the end, you're finding, we're back to this, the absolute min or the absolute max, because usually you're confined to a certain domain, which will come into play for some of the questions, but otherwise it's just sort of running in the background. And then you're going to maximize or minimize whatever it is that we're working on. So I thought I'd start you off with a box problem, see how you do. There's a lot of geometrical shapes like cylinders, which are the can, oil barrel, whatever you want to think about it, like a soda can, pop can. Sometimes we'll do spheres. Sometimes we'll do a lot of the boxes. We do a lot of like three-dimensional, they're called rectangular prisms, but there's boxes. Cubes. We do a lot of fencing for some reason. Those are in here a lot. But I'll just start you with this first one. And this is, again, this document is posted in As You Learn. If you want to pull it up, and if you have the ability to digitally write on it, because I know some of you do that, it's there if you want to, it's there in As You Learn right now if you want to go and find it. But we are maximizing volume. So they're like mini paragraphs every time you have these. You have a piece of sheet metal that's 20 centimeters on each side. And from each corner, you're going to cut a square piece, remove the square, turn the edges up to form a box. What are the dimensions of the box with the largest volume, and what is the maximized volume? So this whole problem, if you pay attention, is dealing with volume of a box. Okay, so and you don't have to be like the greatest artist in the world, and I'm happy to post these. I have them previous classes where I can just post the examples worked out, but I think it really helps if you can draw a picture and label it. Okay, I don't have to see it until you turn your work in, so you don't have to paint like masterpieces, but here's what this looks like, just to give you a visual. You have a square of sheet metal. It's 20 centimeters on each side. They're all the same. And you're going to cut, right? You're going to cut a square. You don't know the square, so I'm going to call it X. And whatever it is, you're going to cut it out. I was using this earlier to practice. I can use this like little eraser tool if you want to visualize. Some of you are very visual. You're going to take and cut out these little square corners, same size, and what it's going to create is this open box like this, right? It's an open box that's really a square. No, it's not really a square, but that's, you fold up the sides and that's the picture that it creates. So that the height of the box is that cutout. And then you have to be able to algebraically represent and find what those sides are. And they're going to be the same, whatever they are, because it's a square. But algebraically, you need to be able to give, like the 20 was this whole side. And you have to be able to algebraically give a representation for that length. So if the whole side was 20, and you cut out an X on this side and an X on this side, the length of that piece that got folded up is 20 take away 2X. Because again, the whole side was 20, and you cut X out this way and X out this way, and then you folded it up, and that's the length, is this 20 minus 2X. So that's like the length and the width, and then the height is the X that got cut out. Did I lose anybody? Because all we're doing is a box. Okay. You can go back and watch it again if you need to. So if we're maximizing volume, do you all remember what the volume is for a box? Volume is like area with the third dimension. And this was more like volume of a, I mean, it's a box. I think they were called rectangular prisms when they first get introduced to you. Does anybody remember what that is? Oh, we got a chat. Let's see what they say. Length times width times height. Exactly. So area for a square, like length times width or side squared, sure. But now that we have this folded up, made it three-dimensional, you're right. It's length times width times height. Okay? So if we are trying to maximize the volume, like that's the goal for the question, like I try to identify to begin with what it is that you're maximizing or minimizing, because that is what you're going to find an equation for. Find an equation with only one variable, because we're not trying to do implicit derivatives here. No, just regular derivatives. So find an equation with one variable for volume of a box. That's the shape we have. That's what we're trying to maximize. So once we have that equation, we can take the derivative of it, find its critical numbers, and one of those are going to be the value that we're looking for. So if we have length times width times height, that is what you're pulling. Oh, that's a pen. Let me do a highlighter. Like this 20 minus 2x, that's like your length and your width, and the x is the height. But really, it's multiplication. The order is irrelevant. But just so you know, the base of the box are the 20 minus 2x's, and then the height is the x. So if I replace all of those quantities with length, width, and height, then what you have is length times width times height. You have a product of some algebraic expressions that have nothing but an x in them. There's not an x and a y. Some equations we have will have that. We'll have to talk about it. This has nothing but x's in it. And I need to take this volume equation, find the derivative of it, find its critical numbers, and then talk about the dimensions of the box. So that's a product of three things. If you wanted to make it, like expand it and sort of simplify it first, that is not a word, simplified, then it'll be really simple power rule. And then you're just factoring and solving it equal to 0. So for these problems where there's polynomials multiplied together, there's 3 products, and I don't want you to do product rule with 3 of them, because then that looks really weird. It's doable, but I think it would just be easier if you could FOIL it out, distribute, combine like terms, make a string of a polynomial, and then take a really easy power derivative. So if you expanded this out, like this and this, that's 400, what is that? Minus 40x minus 40x plus 4x squared. And then that would clean up to be 400x, see that's 80, so minus 80x squared plus 4x cubed. There is the volume formula for this box cut out. Okay? And this is the function that we're going to take the derivative, first derivative, and find its critical numbers and maximize it. Find the number that maximizes it. I mean, that's a cubic, right? If we, what is the derivative for this? So I'm going to do v prime. Or if you wanted to, you could do the derivative of v with respect to x. We had that notation back in chapter 3, I think. It's called Leibniz notation. It's just telling you you're taking the derivative of the volume function with respect to x. That's what this little dv dx is referring to. It's just the derivative of the volume with respect to x. But now we have this really nice, I mean, they're just a string of polynomials. The derivative is one of the easiest things you could find. So 400x, the derivative is 400. The negative 80x squared would be what? Bring down the 2. Negative 160, subtract 1. 4x cubed, bring down the 3, subtract 1. I mean, it's just power rule, like we've been doing. And now your job here will be to set it equal to 0 and find any critical numbers that are going to help us maximize this equation. Okay, it's quadratic. It could have up to 2 things that make it equal 0. Some of them we can use and some of them we can't. So I know the numbers are sort of large. It will factor to begin with if you want to go that route. Otherwise, you have quadratic formula. Some of the questions, this gets harder and you are allowed to graph it to solve it. But this one actually, if you pull a 4 out, this ends up factoring into, like, I think not a minus, something like that. Or if you wanted to rewrite it like 3x squared minus 40x plus 100, maybe your brain processes factoring that way better. I know mine does. I think they're both minus, yeah. However you have to work that out. You have to be able to solve this for 0. And we did this in chapter 3, we did it more in chapter 4, but this one is just, it's polynomial. So if you can get it into a product of things that equal 0, again, the 4 is not really helping us with any kind of solution. You get an x value of what, 10, or if you add the 3, divide it, what's that going to be, 10/3? Which is what, 3 1/3? Is that what that is? Those are your 2 options for this, solving that derivative equal to 0. So I guess my question, and going back up to this original photo, can you use an x value of 10 to cut the squares? You might see a problem with that. There's only 20 centimeters sheet metal to begin with. So if 10 were the length of the square you cut, do you might see a problem with that? Oh, chat, I wish y'all would talk some more. It does make 0, Mary Gray. You will not have a box anymore. So if you take a 20 centimeter sheet metal and you cut 10 in this way and 10 in this way, you have no more box. So even though it's a solution, it is not going to be a value that's going to help maximize volume, because it will make it no volume. Okay? So even though we get it as a critical number, we won't use it, because if we plugged it in to this 20 minus 2x, our length and our width would be 0. And we can't have that. So it's a good thing we have a second critical number. So we will use an x value of 10/3. Or if you want to, you can do 3 1/3, but I don't think Sapling takes mixed numbers. So leave it 10/3 and don't make it 3.3. It won't be exact. You need to leave it exact. But that's the length of the little cutout piece that's going to maximize volume for this. Okay, so the question that we were answering, if you go back here, it says, in a different color, what are the dimensions of the box with the largest volume? So what's the length, what's the width, what's the height? And then what is that maximized volume? So if the height that we found was 10/3, then how would you find the length and the width? Anybody want to participate?
Plug them in.
Plug them in where?
Like plug 10/3 into x for 20 minus 2x.
Yeah, because those are the same sides. So if you plug them in to the length and the width, like the expression that you made for them, then you can get that this is 20 minus 2 times, like it's, I'm not going to do it twice. It's literally the same number. But you need to be exact. So if this is 20 minus 20/3, I think it ended up being like 40/3, or what is that, 13 1/3? for length and for the width. That's what the number ends up being. And sometimes they're repeating decimals and sometimes they're nice, like 14.5, but this just happens to be thirds. And that's okay. But there are your dimensions. The dimensions are, let's see if I can get something that matches this. The length and the width and the height are, and for me, it doesn't really matter the order. You'll just have to watch what the question in Sapling is asking for. It is a, where did it go? 40 over 3 by 40 over 3 by 10 over 3 as far as the dimensions are. The length is 40 thirds, the width is 40 thirds, the height, the cutout is 10 thirds. And then the second question that's asked here is, oh, let's go purple. Oh, it's too close. Go blue. What is the maximized volume? So if you pull the volume and you actually take and do that product of 40 thirds times 40 thirds times 10 thirds, it's something over 9. What is that? Is that 16,000? Right, 3 times 3. Just kidding, it's over 27. I can't multiply. Right? And then 40 times, can't believe I'm really typing this into a calculator. Yeah, 16,000 over 27, which doesn't really, I mean, it doesn't simplify. So you could leave it that. It's approximately 592.6, what would this be? Cubic centimeters. But I think your homework asks for exact, imagine that. So the 16,000 over 27 cubic centimeters would be the maximized volume. Okay, so we did dimensions. The dimensions are here, and then the maximized volume, whether it's the exact or the fractional or the decimal, it'll tell you what kind of answer it wants you to give. But it's a pretty popular calculus question about maximizing volume on a box. And sometimes it's a square piece of sheet metal. I think I have another, one of the ones I'm going to get you to do for a take home to try it this week is a rectangular piece of sheet metal, but that's just going to affect, instead of being 20 and 20, maybe it's like 30 and 40 or 57 and 25. I don't know what it is, but they change. So that would change, you know, all of this, but the process is still the same. You set up the formula for volume, make sure you only have one variable, clean it up, take its derivative, find its critical number. And again, there's not really like, you don't have to make the box and go above and go below and test it. That's going to be the value that maximizes it. Okay. Are there questions on this problem? Because this was honestly an easier one. You follow all of it for the most part? Yes. Well, they can get ridiculous, but we don't do those. Yeah, we're going to do the easier ones. So even though you may think some of them get hard, you need to truly appreciate the fact that these get outrageously hard and we're not going to do those. That's why your homework only has 10 questions on it, because we're doing the easier ones that the book has provided through the publisher. But I do want to show you a harder one with the 10 minutes that we, well, 13 or so minutes that we have left. So I'll show you this one, but we might do a geometry one. Well, this is geometry, but so I'll read you this one and we might come back to it. We could do it tomorrow. So another really popular optimization problem is minimizing cost to produce something. And a lot of the times it's a cylinder shape. They make me think of soda cans or oil barrels, just because I grew up around those and that's what we used to burn things in, were barrels. And feed things out of on a farm. But anyway, you have, usually you're given some measurement, like this one happens to give you the volume. The capacity is 100 cubic centimeters, that's a volume. And this is actually one of the more involved questions because it's minimizing a cost. So in the end, you come up with like a cost function. And so you have to build this cost equation, but it has to deal with Like in this case, it's a cylinder, and you're trying to make the top and the bottom material is 6 cents a square centimeter, and the container, I like to think of like a soup label around the outside. It's material that's only 3 cents per square centimeter. So you basically find the radius and the height that will minimize the cost to produce this container. So all of that, where do you ever learn how to do this? It is optimization, absolutely. But the reality is you go to companies and you work for them, and there are programs and they do it for you, but you still have to understand it. I might come back to that one. I want to do this one, because another popular one is fencing. For some reason, people have fence to work with and they want to try to maximize area that they can. I mean, it's very applicable for farming. You know, if you have so much material that you're working with because you don't want to go buy more, or you can't because you're not allowed at the store because of the coronavirus, you have to use what you have and try to figure out the dimensions that would maximize the most, you know, give you the most area that you could do whatever you're trying to. Put a crop, put an animal, build a shed, who knows. But they look like this, and then here's one where you've got a motel owner that's trying to do a plot on a highway. So we'll do this one. Yeah, we'll do this one, and then I think we'll probably run out of time, but we're going to try this one, and we'll do more tomorrow. So we'll start. So it says that a farmer has 4,000 meters of fencing, and they give you this nice picture. A lot of the times, 9 times out of 10, there's no picture, so pictures are much appreciated. You want to enclose a rectangular plot, so that's some words that are coming here. 4,000 meters of fencing. You want to enclose this rectangular plot. It borders a river. They don't fence along the river, so here's the kicker. What is the largest rectangular area that can be enclosed? So your job here would be to understand, I mean, I know that this is titled Maximizing Area, but it's an example from your textbook, so it gives it a title. When they show up on sapling, homework, quizzes, tests, they're not titled. So you have to be able to pick that out from the information that's given to you. So if you're trying to find the largest rectangular area, then that's exactly what you're doing, is you're maximizing area of what shape?
A rectangle.
Yeah, an area of a rectangle, length times width. Look at that. That's in 3rd grade right now, apparently. So, ridiculous. So you are ultimately trying to find an area formula for this situation, and then we're going to take the derivative of it and find its critical value, and that will be one of the dimensions. But length and width are 2 variables. I don't know either of them. This one uses x's and y's. So you can use the x's and y's, or you can use l's and w's. It doesn't really matter. Just you have to know what it is that you're solving. We can use x's and y's. But for right now, if I want to do the area of this rectangular plot, it's x times y, and that's 2 variables, and that's a problem. So you have to look at the other information that's given to you. The only other numerical information that's given to you is the 4,000 meters of fencing, and that's not the area. That is, you have 4,000 meters, and that 4,000 meters needs to span the perimeter of that image. Okay, so the 4,000 meters that you have, it's going to translate into the perimeter that's allowed for this setup. Okay, and normal perimeter for a rectangle is, it's add up all the sides, right? It's usually twice the length plus twice the width, usually in a normal rectangle. But now that this rectangular plot is being put up against a river, and we don't need the 3rd side, you can look at the picture, and if you add the 3 sides up, the perimeter here is the x and the y and the x again, or 2x plus a y. Like, there's not twice a width and twice a length, it's just add up the 3 sides. And the number that you know is that if you add up those 3 sides, it will equal 4,000 as a given perimeter. So what we'd like to do is maximize this area of x times y, or length times width, but we need to express this with only one variable. Like I only need to have one letter in here, and right now I have an x and a y. So I'm going to come back to, let me get some other, I'm going to come back to my perimeter setup, and I'm going to use that. And you see how you have a 2x plus a y equals 4,000? If I solve this for the y and get 4,000 minus 2x, then what you can do is take this expression and replace it so that now you have area equals x times 4,000 minus 2x, and it's in terms of x. Okay, so the majority of these, you have two equations that you set up, the one that you're trying to optimize and the other stuff that you're given. And the other stuff that you're given will have a way for you to solve for one of the variables and plug it into the other one. And it works out nicely. So I said step one is the hardest part of this whole entire section, because you have to be able to set this up. And the only way that you're going to get better at this is to do your homework now and start it and practice it. Okay, so our area formula, if we distribute and clean it up, is 4,000x minus 2x squared. So this is the formula that we want to maximize. So we'll take its derivative, we'll set it equal to 0, we'll find its critical numbers just like we did in previous sections. So you can either do a prime or you can do the derivative a with respect to x. It's kind of the same thing, just different notation. But this is power rule again. 4,000 minus 4x, and then we have to set it equal to 0 and solve for any critical numbers. I really want to get rid of all this, whatever this is. Like my whiteout, it's my ghetto iPad whiteout. It's office figure, I don't really care about all this crap. Okay, just needed more space to write. So if you set 4,000 minus 4x, oh, that's really fat. Try that again. 4,000 minus 4x equal to 0, right? Add over the 4x, divide the 4. Where are you at? The width is 1,000 meters. So that's this width. The length, had it asked you for that, because it doesn't really ask you for the dimensions, it asks you for the area. But you could plug that back into over here, right? 4,000 minus 2 times x. So 4,000 minus 2,000. So the length is 2,000 meters. So the area that gets maximized is 2,000 meters times 1,000 meters, which is 6, 2, 3, 4, 5, 6. Is that 2 million square meters? There you go. That is the largest rectangular area that can be enclosed. Yeah. 1, 2, 3, 4, 5, 6. Okay, zeros. They get me. It's that easy stuff. Times 1,000. Yeah. Questions? These are a lot. These are like fill up the whole page with math problems. And the biggest part will be the initial part where you have to set it up. And they literally, you have to practice them. If you don't practice them, you know, like when I gave this test last semester, these were take home because I know they take longer. So, but you have to practice them or you're never going to get them. Questions on any of this? Because the one with the fence at the motel is pretty similar. You can rewatch it later, take it, process it. I'm going to go to another slide just to trying to think if it were. No, that's another one here. So yeah, this is the minimizing cost one. Any of these cylinder ones involve pi, and your answers are going to be exact. And so again, they're like little tiny stories, and then you have to weed through it all to find the dimensions that's going to minimize cost. So, and I know it's labeled that, but they're not always labeled that. So what you have to find is basically a cost formula. And it's just going to be a certain price. So this is a cylinder where you have a top and a bottom, and you have the label on the outside. So if you're going to minimize cost, you have to be able to do, so the cost equation is going to be the cost for the top and bottom plus the cost to produce the sides. Like that's the formula that you have to come up with. It tells you the price for those, but this is a surface area problem, right? If you're gonna label something and look at surface, it's called surface area. And we do cans or cylinders. I have seen a sphere. I haven't really seen many pyramid questions. Maybe a cone. You know, like imagine a waffle cone that has the little paper wrapper. Somebody somewhere came up with how to minimize cost using calculus in the background. And that may never be you, and that's okay. But we'll have, I think we're almost out of time. We'll come up with this cost equation tomorrow, but it will have to do with surface area. So they're very formula based. Even the one with the square in the box was a volume area. This one will be volume, surface area, rectangles. We have a few that's going to use the distance formula. I don't know if you guys remember the distance formula, but we'll talk about it. But we'll minimize the distance between a point and a parabola. You know, like if you had a parabola and you had a point, you want to minimize. There's lots of distances you could take, but we're going to end up finding the shortest distance from a point to a line using the distance formula. But there'll be lots of examples. I don't know if we'll get to this one or not, but anybody have questions? Is that enough for one day? They're really not that bad, the optimization problems, but I can't stress enough the difficulty will lie in your ability to build the problem. And that's what, if you can start it today, I would start it today. I would absolutely start it today. I can post answers to some of the problems that we haven't done yet. I think I have them. And we can do that, but you let me know, and this is recorded. I'll post it if you need to go back and watch it later. Email me if you have questions. I'll be doing some third grade, first grade something here for the next hour or so. But later this afternoon, if we need to get back together, just reach out and let me know. Okay? Okay, good luck. Let me know if you have quiz issues too. Well, I'll get them graded. It'll just, I gotta sit down and do it. But I'll see you guys tomorrow.